Today's Daily Dose of Math is just a brief intro to some functions language and some functions notation. Students, as they learn math, learn how to graph a straight line. Here I have two straight line equations, y equals 2x plus 1 and y equals x minus 5. Both of them are in the y equals ax plus b form, and I can graph them by making a table of values. So I'll go ahead and do that. If x is 0 in this first one, y equals 2 times 0 plus 1, which is 0 plus 1, which is 1. And I have my first point. If x is 1, y equals 2 times 1 plus 1, which is 2 plus 1, which is 3. And if x is 2, y equals 2 times 2 plus 1, which is 4 plus 1, which is 5. And I can graph this. I put dots at 0, 1, 1, 3, and 2, 5. And I draw a line through those dots. I make sure the line goes all the way through my graph to show that I understand that it actually keeps going. It doesn't just stop after it gets past these points. I have successfully graphed this, and I can label it. I can write the equation y equals 2x plus 1. The second equation I can do the same way. Y equals x minus 5. If x is 0, y equals 0 minus 5, which is negative 5. If x is 2, y equals 2 minus 5, which is negative 3. If x is 5, y equals 5 minus 5, which gives 0. And I can put those dots on my graph, 0, negative 5, 2, negative 3, and 5, 0, and I can draw a line through those. Making sure to draw the line all the way through the graph. Okay, so if I want to use functions language and functions notation, I can say that I have two linear functions. Both of these are functions because they're straight lines and they're not vertical. That means that they are qualified as functions. I can change the name of the function a little bit, change the equation, what it looks like, by removing these y's and renaming them as f of x and g of x. So one of the useful things about this little functions notation is it allows me to give different names to the different equations, and that can make it a little bit faster to label the equations on the graph. I never wrote the second equation on the graph, but I'm going to change that. I'm going to say this is f of x, and this one here is g of x. So that's a useful thing. We get used to saying f of x instead of y. But it works the same way. When I make my table of values, if I want to know the point where x is equal to 0, f of x equals 2x plus 1, I can write f of 0 equals 2 times 0 plus 1, which is 0 plus 1, which is 1. I'm getting the same answer. I'm just not calling it y anymore, I'm calling it f of x. But this is very useful too in the notation. Writing f of 0 helps us to see what it is we're doing. What we're doing here is we're taking our relationship and we are plugging x equals 0 into it. And we say so right as we start writing down the calculation. That's useful. Then you get used to being asked questions using functions language, like, what is f of 1? Well, if a question asks me what is f of 1, I'm doing the same thing that I did right here when I found out that when x is 1, y is equal to 3. I'm using functions notation though and I'm saying, oh, that's equal to 2 times 1 plus 1, which is 2 plus 1, which is 3. Same answer. But I'm saying it now with functions notation, and I'm using functions language. Well, of course, I can also answer a question in a similar way for g of x. So I can write, for instance, g of 4, which is not one of the points I found the first time. G of 4 has to be equal to 4 minus 5, which is -1. I just found another point that I could put on my graph if I want. And I can see the difference between the calculations that I did for my f of x and g of x because I'm using the letters as a name. So functions language and functions notation allows us to have a language and notation that makes us more organized and makes it more clear what we're doing. This is an advantage to the student as they're learning, and it represents a new way questions can be asked, which is still not difficult for us to do because now we understand the language. And one more thing, I've renamed my functions, so I'm not using the y anymore in the equation, but I still have y's here in my table. I can remove those y's, and I can write f of x here. But I'll write g of x here. This is commonly done in tables of values when you're using functions language and functions notation. Then, what about this y that I use to label my y-axis on the graph? Should I replace it with f of x? But wait, I don't only have f of x on the graph, I have both f of x and g of x. Should I just leave it as a y? Yes. F of x and g of x are the functions in this situation, but y is still the dependent variable. When I first learned functions language and notation, I couldn't help but think it seemed to me like the function was like a little machine. Like you have a set of conveyor belts that goes into the machine, and you put raw materials on one end of the conveyor belt, and they go into the machine and they're transformed into a product. And when they get outside on the other end, you have transformed your raw materials into some product. I see this functions notation as a way of seeing the function equation as like a machine. I'm plugging a 0 as my x, as my raw material here, into my machine, and it's giving me a 1. I'm plugging my 4 as a raw material into this machine, and it's giving me a -1 as the product. That's a cute way of seeing how this works, which helps me to remember how it works. And these are tricks that we do when we're learning that help us to learn better. Functions language and functions notation are very useful, and being able to read them and understand them when they're being used in a question is extremely useful to a student. That is today's Daily Dose of Math. Please like, subscribe, and share.